This conference will now be recorded.
In this brief discussion today, I would be discussing about what are the uses of control system in our life and how can we uh, uh, pose a control problem and can be solved, and we can also solve by using the available softwares, especially MATLAB. So the main question which is there for us, why to study this subject? And the simple answer for this, one second, my slides got stuck. I don't know. One second. So let me just check. Yeah, now it is fine. Yeah, so every system of today has some kind of control engineering involved in it, and there are numerous applications around all of us in our daily life. So here are some of application of control system like AC, refrigerator, the pump in our toilets, car driving, drones in industry, and many more. So there are many application of the control system where we require some of the tools or fundamentals from this subject to study these kind of systems. So basically, there are two kind of control system which we encounter in our practical life. One is referred to as the manual control system, and the other is the automatic control system. So in manual control system, a system that involves some kind of person controlling a machine is referred to as manual control system. For instance, driving an automobile or switching on or off of a fan or a light bulb are referred to as manual control system because there is some kind of human involved in these tasks. On the other hand, a system that involves only machines and sensors is referred to as automatic control systems like AC and the home room heater, electric iron, etc. are some of the examples of automatic control system. So we can understand this concept by this diagram. So this we all have experienced when we go for shower in winter season. So what we used to do, there is a wall or we have the taps, and we are getting both hot and cold water, and we have to set it manually to get the water at the desired temperature, right? By which we can take a shower. So this is a kind of manual control system. On the other hand, suppose we have some kind of temperature controller. It's a kind of sensors which sense the temperature of the water which is coming from the shower, and according to that, whatever desired temperature we have set for this temperature control, it will give the control command to this valve automatically, and finally you will get the water at the desired temperature. So this is referred to as automatic control system. And this course is actually about the automatic control system, uh, in which you will see how can we control some systems automatically. This automatic control system is further classified in two domains. One is referred to as open loop control system, and the other one is closed loop control system. So in open loop control system, we just control any system by some pre-set controller. For instance, if you take washing machine is a kind of open loop control system. Since when we put the cloth inside this, we set at the uh, function of or the limit of the washing machine at some level, and it will automatically end at that point, and the intermediate processes will be of some limited time which is preset in the washing machine. Similarly, the on and off of the traffic light are also an example of open loop control system. While in the closed loop, feedback control system or the closed loop control system, we have some kind of feedback or sensing device by which we actually compare what is the difference between the actual output of any system and what is the preset value, that is also referred to as a reference value. And by measuring the difference between the desired and the actual output, we actually generate the control command. So in most of the system, we usually have the automatic control system, this closed loop automatic control system. And there is one problem with this automatic control system, which is this. So usually the automatic control systems are accused of taking away jobs of human. So this accusation is actually true and false at the same time, which we can understand by some of these benefits of automatic control system. First one is the in the cost saving. So I took this example of an engineer, Niels Gustav Dahlin. He is a Swedish engineer, and in initial days of his life, he was working at this lighthouse, and his job was just to light some kind of fire so that the ships or buoys that are coming or going from this region, they can get any kind of signal, some kind of signal. So his job was very tedious, and he has to wake up midnight and he has to continuously monitor that is there any ship or buoys which is coming or going. So his job was very hectic, and he decided make to build some kind of automatic system by which it can it can autonomously or automatically generate the light. So his discovery is actually referred to as this sun valve. So it's a kind of automatic regulator. It's a automatic which is used for illuminating the lighthouse for the buoys and the ships. So for this discovery, he was also awarded the Nobel Prize in year 1912, and he proved that by using such kind of automatic techniques, the operational cost reduced reduced by a factor of 400. So this is one of the advantages of automatic control system. However, unfortunately, in this discovery, he lost his eyes. But this was a great discovery for the human beings, for our society. Other than this, there are many advantages of automatic control systems like reliability, precision, accuracy, and finer control, doing any job repetitively, tirelessly, and operations in risky situations where any human intervention is not possible. However, if you see that in this block, there is one quote which says that the unwritten axiom of engineering system is that they break. So they need to be maintained properly, and humans still have a job, but of different nature, which is less critical, right? Because machine fails too, and to control the machines, we finally required a human. So this is some of the background of the automatic control system, and here are some modern applications of control system in multi-agent coordination and control. So in which you would have seen that when we fly many drones or unmanned aerial vehicles, so we have to design some kind of proper control algorithm so that we can achieve some kind of desired objective that can be completed by these drones and unmanned aerial vehicles. So here is one cartoon which I have taken from Wikipedia or Google. So you can say that the couple came for some dinner party, and this now the waiter is showering the flower by controlling this drone. So from drone the flowers are coming. So it's just a cartoon to to make you understand that the automatic control system is one of the essential part of our today's life. We also have many application in a smart healthcare. So in this pandemic situation of COVID-19, making automatic ventilators, completing many tasks by robots, because we need less human intervention. So in that case, automatic control system is one of the uh, dominating field among all in current scenario. We also have applications in a smart power system, smart transportation systems, economics, sociology, and cyber physical system, advanced space technology systems, and many more. So you can see that there are many applications in which we can use the tools from the control systems. Here is a brief slide. So in which, if you see in the current scenario, for many defense and civilian applications, we want that, suppose there is any, we want to surveillance across the territories of two countries or of states. What we do, we just send some kind of a small unmanned aerial vehicles. They make some kind of formation, and then they just search or inspect that area. So there are many applications like surveillance, search and rescue, tracking and monitoring, spacecraft formation, oil spill tracking, where human intervention is not required and or not desired. So in those applications, we need that the task to be completed automatically, and that can be done by the tools from the automatic control system. So just to conclude, what is required when we study any system? The first part is we just model our system, and the second part is just after modeling, we design the controller for this system to achieve the desired objective. So modeling, in the sense, modeling is nothing but representation of the system's behavior in the form of some differential equations. So this, I just have in this slide some kind of robots which are referred to as omnidirectional robot or two-wheeled robots, and they can be modeled by using some kind of differential equations, which those are written over here. So once we have these differential equations, the second objective of the control system is to design the control. So suppose in this second figure, v is the speed of this robot and omega is its angular rate. So we can design these speed and the angular rate in such a way that this robot move or behave in the desired way that we want. So here is one problem which I uh, solved during my as part of my research work. So here your objective is that you have some kind of desired circular orbit, means the radius and the center of this circle we can choose as per our requirement. And we have some kind of unmanned aerial vehicles, and we just want them to send to this circle in an automatic manner. So how can you design the control for each of the vehicles so that that controller will give the command and the vehicle will reach to this kind of circle, desired circle. So in this case, you first can design what you can first define what is the differential equation, means the model of your system. And when we have the model, then you can design the control, right? And the standard control problem here is that suppose you want this, you can pay your attention on this vehicle in the red color. You want to send this vehicle from this position to this on this desired circle. So this is actually the error which you would like to minimize to zero, right? So this is the standard control problem in which you have some kind of error between the desired value and the actual value. So by minimizing this error, you can achieve your objective. So how, but the question here arises, how can you minimize this error? This error can be minimized by using different kind of controllers. And if you have heard about this PID controller, proportional plus integral plus derivative controller, which is one controller by using which also you can minimize this error. Other than that controller, there are various kind of controllers one can use in our to control the system to meet some specific requirements. So when we design these kind of controllers and algorithms, then how we just verify these algorithms? That verification is usually done in MATLAB, initially in some kind of software, and in control system we usually use MATLAB. And after the implementation this done through the simulation, then we will implement on the real system. So here is one simulation result which I have. Just I will just show you one simulation result, one animation basically, and you can see what is happening in this animation. See, this animation was done in MATLAB by using the MATLAB software, and you can see that all the agents, this black one is their centroid, and all the agents are moving in such a way that they will finally, their center is going to the desired location, this which is marked in star. So center is going to the desired location, and all the agents are finally moving on the circle, you can see. So these kind of formation implementation you can do in MATLAB just to check whether your algorithm is working or not. And then finally you can implement on the real system in the laboratory environment. So with this, I just would like to conclude that control system is one of the essential technology of present scenario, and we all should know about this about the techniques and the tools that are used to control any system. So thank you for your patience and listening this. If you have any questions you can ask to me. Thank you very much.
One or two quick questions we can take. If anybody is having any questions, please put it in the chat box, and I will moderate and I will ask the same questions to Professor Anu. Okay. Okay. Thank you, Anu, for the fantastic invited lecture for our for our STP students, and thank you for enlightening us about various control techniques, their applications, and the usage. So thank you very much. Thank you.
Thanks Bernie. Thank you.
Yeah. Thank you. Thank you.
Okay, yeah,
See you.
bye.
Okay. Bye. Bye. Okay. So good afternoon, good morning, good evening, everyone, whichever part of the globe you are located at. So today we will be discussing about the first topic, which is the introductory lecture on control systems design. So my sincere request to all of you is to please be on mute so that others will not get disturbed. If you have any queries, please keep it in, please put it in the chat box. And the another request is all of you please keep your names as I told, SDP dash, whatever the name you have. I can see that some still Aisha, Aistu, Del, Vinay Kumar, Gayatri, Jasmine, Niharika, some Microsoft account, Pattabhiram, Sweta, Pavani, Shyam Babu, and whoever has not kept, I will be removing you in another 10 minutes. So please, all of you, please, I am requesting all of you to please rename your whatever the display name as with SDSDP1, whatever is the other continuation, hyphen your name. If you're not keeping your name, if you don't change the name, I have to forcefully remove you. Please, it is okay. Okay. So thank you. So thank you all. So I'm giving you another 10 minutes of time. Please rename yourselves as SDP1 triple X, whatever your number is, and hyphen your name. Thank you. So I'm giving you 10 minutes. If not, then I will remove it. Thank you. So let me share my screen and I will be telling you what we are going to cover today. And all of you, please be on mute. So all of you, please be on mute. So, okay. So today we'll be discussing, we'll have the Twinkle, please be on mute. So today I will be discussing on the introductory lecture on control system design. And this is the first day. And myself is Bharani Chandra Kumar, and I am a faculty at GMR Institute of Technology. You might have seen my profile in the flyer, so no further discussion is required in this aspect, I think so. So, the thing what the Anup has briefly discussed is about various aspects of control systems and their application. I will go in a very different way. First of all, what I will do is I will just brush up if you are aware of the control systems and what is it and how we do it. First of all, we will brush up some of the fundamental things and then we will go into much detailed things. So today, for the first half an hour, it could be kind of brush up things, which you might have already be aware of. However, as time goes, we'll go into the very detailed discussion. So what is a control system? So the objective, the main objective is to control the output by varying the input. If you see this block diagram, so this is the overall block diagram. So this control system consists of several systems, sensors, actuators, and error detectors, and so on. So, the objective of the control system is to control this output variable by varying the input. For example, let us consider a very simple case of DC motor. And I assume a very simple scenario where the voltage is directly proportional to the speed. So the output there is the speed which I want to control. How do I control this output, which is the speed of a DC motor? By changing the input or by changing the input voltage. And inside there are lots of things. Controllers will be there, and tachometer or some kind of speed sensors will be there, and several things will be there. So this is the fundamental objective of the control systems. There are two types of controls. One is open loop control and the second one is the closed loop control. So you can see that this is the plant. The plant means it can be any system. It can be motor, it can be generator, it can be DC, it can be pump, or it can be aircraft or any kind of thing. This is the output. The one which is going to the plant is called as control input. And the control input from where we are getting the output of the controller is the control input, and the difference input is going to the controller. That means, suppose in a very simple case, let us assume if I want the speed of uh, let us assume that if speed of 1200 rpm here. So what I mean to say here is, so the reference input is 1200 rpm, and I have some feed forward or open loop control, so which has, based upon this input, what I will say that if the reference speed is 1200, then the corresponding voltage, let us assume 120. So what I will do is, this controller is kind of a static mapping between the speed as well as the speed and the voltage which is going to the DC motor. For example, if I say that in a very simple case, the static mapping is 1:10, or 1 is to 1 by 10 or something like that. For example, if I want the reference speed of 1500, the input voltage should be 150, or so on. So that is called as an static control or feed forward control or open loop control. So which, if I know the exact relationship between the input and output, then I can, there is no need of the feedback. But in the realistic systems, this open loop control will not work if the system has uncertainties, and if you don't know exact behavior of the plant or the controller or the various external disturbances, then this is not going to work. So these open loop control, mainly they are the time based control systems. For example, the fan, a typical water tank, and timer based traffic lights. Why we are calling this fan as the open loop control? Because this fan does not it does not sense the temperature of the room, and accordingly it will act. Suppose if the room's temperature is 40 degrees, then fan does not have, in a normal case, the fan does not have the tendency to, to change the speeds automatically based upon the room temperature. However, an alternative is air conditioner, which we will discuss in the next slide. And the typical water tank is also a uh, an open loop control. That means, so what we are doing here, just manually, there is no such feedback mechanism in these things. In most of the cases, what we do is, when the tank is empty, we'll keep the switch on for 5 minutes, and then we switch it off, and we assume that in the 5 minutes the tank and we as and we assume that in the 5 minutes the tank will be filled, and automatically we switch it off. However, the problem here is, we never know, what is the actual level of the water tank. Is there any water is already there in the tank, or is it overflowing? There is no such mechanism. We are not doing any kind of feedback thing. And another example here is timer based control. In the timer based control, what we are doing here, timer based traffic lights. So in this particular application, what we are doing is, just it's not based upon the density. Suppose if nobody is there, uh, if nobody is there as well, so the timer will be on. So suppose the green lights and the red lights, and caller 143. Just give me a minute. I will just remove that caller first. Okay. So sorry for the disturbance. So the time-based traffic control, it does not take care of the density. For example, if the density is more at one particular channel, or in one particular road, then it should give more preference. Then the light, then accordingly the green light should be given more preference as compared to the other routes. However, in the typical open loop traffic control systems or the traffic lights, it is just the time based. So for a minute, one of the things will be on. For 1 minute, for a minute, for 1 minute, if something is on, and for another minute, automatically the other will be off. So it is completely the open loop thing. So which completely time based. So in general, if the control systems are time based control systems, we call it as open loop control. So timer based control system. However, we will see how we can convert each of these examples, what we have seen, the open loop to the closed loop, and what are the advantages and what are the disadvantages as well. We will look into that one. So before going to the detailed this diagram, which is called as a closed loop, or sometimes it is called as a feedback or closed loop system. So you can see that this is called as a feedback loop. So this feedback, in the presence of this feedback loop, if it is there, then we call that kind of systems as closed loop systems. So now let us assume what is going to happen. We'll consider the same DC motor. So where the output, let us assume the reference input, or if I want the reference speed as 1500 RPM. However, your actual speed is, let us assume, 1200 RPM. So the speed sensors will sense, and 1500 minus 1200. So this is 300. 300 RPM is the error, and that error has been given to the controller, some kind of voltage controller, and accordingly, the voltage controller should give the corresponding input, corresponding voltage to the plant. So the main purpose of this closed loop plant is to make this error as zero. So if this error is zero, then what is happening? This reference input minus the output equal to zero. Sorry, equal are the same. So if the error is zero, then the reference input minus the output equal to zero. Hence, reference input is equal to the output. That means the 1500 RPM is my reference input, and the reference speed what I want, and the output is also 500, 1500. If there is some error, this controller will activate and it will keep on giving the voltage accordingly. In some of the cases, if the error is more, then more input is required to stabilize the plant. If the error is less, then the less control input accordingly is required for the plant. So as we discussed the open loop plants, so the open loop control. So now we will see the closed loop control, how it is different. You can see that in the domestic applications is also, you can, control system is everywhere. You cannot say that this control system or that control system and so on. So control system is everywhere. So this air conditioner is one such example of the closed loop control system. In the fan, what we are not measuring the room temperature, and we are not and we are not sensing any temperature of the room, and accordingly, just we kept it on or off. That's it. We don't have much control. Only you can regulate the manually the speed. See, nothing more than that. So there is no complete feedback mechanism in that. However, in the air conditioner, going to happen, what is happening here is, suppose if you want the temperature of this room to be 20 degrees centigrade, then what the air conditioner will do here is, if the temperature is more, suppose if the current room temperature is 30 degrees, then the error is 10 degrees. So accordingly, it will keep on and off the compressor accordingly, so that the error will be zero, and hence the temperature of the air conditioner will be maintained at 20 degrees or the desired one. Though it may take some time for that one, due to the various environmental factors and other factors. However, it is an auto. Everything happens automatically. Just you set the reference temperature as 20 or 25 or 15 or whatever may be, and accordingly it will give you, so accordingly it will operate, and it will keep the room temperature at the corresponding, whatever the desired temperature, whatever you specify. So the another such kind of example is density based traffic signals. For example, as we discussed, if there are, suppose, let us assume two lanes, and in each of the lanes, the density is in one such road, the density is very high, and in the other parallel road, or the other corresponding road, if the density is less, then the more priority should be given to the density where the density is more, or the green light should be accordingly switched on based upon the density. If that is the case, then yes, then that becomes a closed loop control, and the people don't have to wait for more time there. So optimally, effectively one can utilize the time, and hence it is more customer friendly, and it will be more economical as well. So, and another such examples are aircraft, launch vehicles, missiles, electric motors, and so on. So in almost all of these cases, one always need some kind of there is some kind of closed loop mechanism involved in that one. So as we slowly keep on going, we will have more focus. We'll be discussing this DC motor application in very detail, and how to do the simulation and so on. So this is just the preliminary things what I'm discussing here. So this is another example why control systems. So first of all, just see what are these. Just take a few seconds to see what are these two figures, and then I will explain you. Okay, so I will tell you what are these two figures. So this is the source is AUSI, Autonomous Undersea Systems Institute. So this is a vehicle which is an autonomous undersea vehicle. The task of this vehicle is to explore the sea undersea. So what is there? What is the flora? What is the fauna? And what kind of what is there any special things available in the sea, inside the sea, and other things? So this is such vehicle which will autonomously, uh, it has to travel and it has to do certain applications, certain operations. So if you see, the interesting thing here is there is this, you can see the solar panels. One can ask why these solar panels are required. The simple answer is, if you want to propel this particular for a very long range, suppose for 1,000 kilometers, there are two things is required. One thing, either you should store, you should have such so much of propellant in it such that you can propel it for 1,000 kilometers. Or the second thing, propellant means either it could be the electrical energy saved in batteries, it could be, or it could be, diesel. Or so the problem there is you have to carry so much of fuel with you, and this is a very lightweight vehicle, so nobody wants to carry the fuel with it. The another way of you know of moving this particular vehicle in the 1,000 kilometers in the sea is by connecting a cable of 1,000 kilometers, and through that cable, if we can able to supply the power, then that is also fine. But both solutions are not viable. So both solutions has its own problem, disadvantages. You cannot carry so much of fuel, so that you will be it will be very bulky, very heavy. And the second thing is also, you cannot have 1,000 kilometers wire to supply this one, to supply the small vehicle. So the idea here is, can I use the solar panels? The solar panels, what they will do is use during the daytime. It will charge themselves. It will charge the batteries, or it will save some kind of energy. It will convert solar energy to the electrical energy by in, or it can be saved in batteries, and that can be used during the day and night times. Uh, so that is one such applications. And as long as there should be some mechanism, as long as the battery's charge is very less, then if it is under vehicle, then it should come out and it should charge accordingly. So this is an autonomous undersea system vehicle, but a bit advanced one is autonomous sea vessel unmanned marine vehicle, which is in the bottom. So you can see that it is a combination. There are three combinations. There is a small wind turbine here, and you can see the same solar, and it has own diesel propellant as well. So it is a kind of hybrid, the hybrid propulsion system. So earlier one, the first one has only the solar thing, but this has solar. It can convert the wind energy into the required energy, required power, and solar energy, as well as the diesel as well. So this is bit more advanced than this one, whereas it only uses one, the solar, and maybe some diesel as well. But it, including with the solar, it is using the wind power, wind turbines, which will convert various forms of wind energy to the required electrical energy. So here the problem is where the control system is. The control system is whatever you have designed, it should be capable of doing the autonomous navigation inside the sea or over the sea surface as well. Autonomously means automatically it should move from one area to another. When you say that autonomous, it means that it should have some intelligent mechanism which should avoid the obstacles on its own, and it should follow the optimal path and so on. So that is exactly what the autonomous cars in which now the current trend, every vehicles, everyone is interested in the autonomous cars and so on, which includes the Mahindra, or all almost all automotive sectors are interested, including the services like Uber and Ola are also interested in the autonomous cars and so on. So, so this is another such complex, control systems. Why it is required? You can see that if the control system is not appropriately designed, or if it is not fault tolerant, if something, if there is some fire in one of the wings, then it would lead to the crash or the emergency landing. It will lead to crash. Srividya, could you please be on mute? So, so if an appropriate control mechanism, even you can see that if there is one failure of one of the control surfaces, what you are seeing here is it possible if during the control surface as well, during the loss of the control surface, can I still able to maintain my stability or my desired path or my desired specifications by using the other, surfaces or other redundant control surfaces available with us? So yes, it is possible, and that is the main idea behind the fault tolerant control, where if one of the actuator fails, then how do you recover your performance by using the other, redundant actuators or so on. So this is one such example why the control system is required. And another one is, this is the ISRO's vehicle. So so whatever you are seeing there is then ISRO's one of the ISRO's vehicles, launch vehicle. So there also control system plays a crucial role, because what will happen is, once if you design the trajectory to travel for this launch vehicle, then how do you ensure that it is traveling in the trajectory? So that the trajectory is nothing but the reference input, what we have discussed of 1500 rpm for the DC motor case. Yes, but here it could be the reference could be the trajectory or the path in which this launch vehicle should travel. So the control system should ensure that the launch vehicle should travel in the trajectory itself. If it is not, then there is a possibility that it might crash as well. So the control system plays a crucial role in these applications as well. So a real life control systems, a typical flow. So what I mean to say here is that as far as the real life control systems are concerned, so what is the step by step process? Suppose if you want to design a control system for a particular vehicle or particular car, or and if you want to go for the mass production, then what are the steps? The first thing in the control systems, real life control system design, is system modeling. How do you do the system modeling? If it is an electrical circuit, then obviously one can use the KVL or KCL to find the system's model. System models means it is nothing but finding the input output relations in terms of by using the with the help of differential equations or so on. And very simplistic ones are the transfer function, where we assume that the plant is linear and initial conditions are zero and so on. If it is a mechanical system, we can go with Newton's laws, or sometimes we can use the concept from the physics, biology, chemistry, and various other aspects to come up with the system's models, or come up with the differential equations of a system. So that is the first thing. If the system is not available, if the system models you cannot easily calculate or easily can find the differential equations of input output relations by using the standard differential equations, then a method which is called as system identification can be used. What the system identification do here is, the system identification is a very simple concept, where what we try to do is, we assume the system as a black box. That means we don't have any information of the system. We give some kind of input and we take the output, and based upon the input and output, we try to predict the model of the system. A very simple example is, if a black box is given to you, and if the input is cold water and the output is hot water, that means you have only the input and output information. That means input is cold water and the output is hot water. You don't know what that particular block is, but based upon this input and output, you can able to judge that there is some heating mechanism involved in that one. Either it could be some heater or the geyser, or there is some heating mechanism. So this is a very simple example. In a similar way, if the system is very complex and it is almost impossible to find the differential equation of that particular system, input-output relations based on differential equations, then one can use the concept of system identification. And once if we have some system, then the next task is selection of suitable sensors and actuators. That means what kind of sensors you want to use, what kind of actuators you want to use. For example, in the case of speed control of the DC motor, if you want to measure, the first thing is you need some sensors to measure the speed. If shall I go for a very high precision sensor or very costly sensor, or can I compromise on the quality in terms of in terms of the error tolerance plus or minus 10%. If the plus or minus 10% errors is nothing I'm going to lose, then I should not go for the high end sensors. A cheap sensor will do the work. So that based upon the problem at hand, one has to select the suitable sensors and the actuators as well. And then the control system developments comes into the picture. So this control system developments, whatever here we are seeing, is basically the software development of the control systems using the MATLAB or so on. And then the high fidelity simulations. And the high fidelity simulations means, though we start with very simple simulations like very linear model with several lots of assumptions, but that doesn't work for the real life systems. What here you have to do here is, here you have to include as much as possible realistic situation in that particular simulations, and which is called as high fidelity simulation. And then one has to go with hills hardware and loop simulations. So here what we do here is, it is something in between the simulations and in between the realistic the model implementation. In the hills, what we do is, some of the components we keep it as real hardware, and some components we keep it as a software. For example, the plant, or suppose if you want to control the wind turbine of 1 megawatt, very huge wind turbine, very huge. So 1 megawatt, I'm saying, yes, there are some GE has few megawatts of wind turbines, very largest one. So how you will do that one? So you, first of all, if you want to do the Hills test, what you will do is, all sensors, actuators can be the realistic sensors. Instead of that 1 megawatt wind turbine, we generally simulate the high fidelity model of that. So it is a combination of simulation as well as the hardware, which is called as hardware in loop simulation. And the lab scale or prototype development and test. So the next step is, in the lab scale, what we do here is, whatever the big wind turbine what you want to implement to your control systems and other things of 1 megawatt, we will scale down to 1 kilowatt, and we do small prototype, and we do all kind of testings in that one. And once if it is done, then what we'll do here is, if the testing has been done, and if it is satisfactory, then on the full blown development in 1 megawatt, whatever the wind turbine, will do all kinds of testings, all kinds of uncertainties. That means different winds, it will be exposed to various uncertainties, including various temperatures, humidity, various wind speeds, and so on. And all kind of safety and reliability will also be tested. If this step goes through, then one has to go for the mass production. That means, if all these steps 1, 2, 3, 4, 5, 6, whatever is saying is, if the system goes through this one, and if it's successfully, and if the certified engineer certifies this, then one can go for the mass production. So this is the typical real life control systems, a typical flow. So almost most of the systems, most of the control system design follow this typical flow. Here and there may be some changes, but this is a typical flow. And the first thing here is, what we are going to see here is, in this particular lecture, or in this particular SDP, student development program, we will be giving little bit emphasis on this systems modeling, and we are not going this looking this in a very detailed way, and control system development. So one and third, these two are only we are going to consider in this SDP. So the idea here is system modeling, how to get the system model or the differential equation or transfer function for a model. So once, if you want to design a control system, in most of the cases, you need some system model. If it is a model based control system, you need some kind of model or so on. So a typical example how to get a system model, this you might be aware of, but I'm repeating it just for the sake of others who forgot what is this, how to model this one, how to find the transfer function and so on. Just I will take in a couple of minutes. So this is the series RLC motor. The R resistance, L is the inductance, and C is the capacitance. And this is my output. I am the output is across this voltage across this capacitor, and this is the input. So what is happening here is what I'm interested here is the V in. So you can see that V in equal to, if I use the KVL or KCL, then R into I plus L di by dt plus V naught, V out. So V out, you can see that V out, the voltage across this capacitor is 1 by C integral of I dt. And if I rearrange, or if I take the differentiation on the both the sides, and if I shift this C to here, then that will become I equal to C into dV naught by dt. So now this voltage equations, what you are seeing here is, in this equation, if I substitute this I value here, so what this V in will become R into C dV naught by dt plus L into di by dt. So di by dt is means, so C into d square V naught out by dt plus this V out. So V out is fine. So that's what it is happening. So you can see that whatever, L into C into d square V naught by dt square plus RC into dV naught by dt plus V naught. So this is my my differential equations, which is related mainly, which is related in terms of V in and V out. So as per the standard definition of the transfer function, what we can say that transfer function is nothing but Laplace transform of output by Laplace transform of input at zero initial conditions and so. So if I take the Laplace transform of this one, and if I assume that the initial conditions are zero, then my output is V naught and input is Vn. So that's what it is happening. V naught by V naught of S by Vin of S. So how I am getting this one? If I take the Laplace transform of this one, and if I rearrange and assume that initial conditions are zero, then I will be getting like this. So now you can see that I have the transfer function as well I have the differential equation. Once I have the transfer function or the differential equation, this is nothing but the plant model, and accordingly I can have, I can do the control system design for to achieve the various desired specifications. So now when I say the desired specifications, what do you mean by desired specifications? So some of the desired specifications, what you can see from this particular slide is speed, tolerance, optimality, cost, reliability, robustness, and many more. So we will restrict ourselves for our discussion here to the speed in terms of the rise time and settling time and so on, and tolerance, the steady state error, and the optimality. In generally, we want our system to be optimal. Either it should be minimization or maximization. Minimization means we want to minimize the error as much as possible. The maximization means we want to maximize the profit as much as possible, maximize the profit or efficiency. And there are various other measures as well. So this is a standard second order system. So this you might very much familiar with this one. So omega n square, where omega is there are two important parameters which completely dictates the system dynamics as well as the complete performance. If you know this zeta and omega n, the complete time response of the system can be found out. Where this omega n is called as the natural frequency, and this zeta is the damping ratio. So what do you mean by the natural frequencies? Natural frequency means if you, for example, if we consider our RLC circuit, so this R is the one or the resistive element or the damping term which will, which will not allow your system to move in a sustained way. That means if you remove the R from the series RLC circuit, then your system's response will be kind of sinusoid, which is nothing but LC oscillators. You might have heard of LC oscillators. That means if you make it short circuit, then it will behave as LC, and that will be LC oscillator. Then you will have the sustained oscillations, and whatever the frequency of that particular oscillation, we call it as the natural frequency. In another way, what if you include the R, what is going to happen here is it includes some kind of damping, and it will damp out the oscillations, and eventually uh, the sustained oscillations, the sinusoid oscillations will now be damped to the, after some time, all the oscillations will be damped out, and it will be the response will be flat. So this is a typical time domain specification, typical time domain second order, the plant response under damped. So this I have taken from the Norman and Nice textbook. So wherever the contents from wherever I have taken the sources is written in the bottom. For example, this particular example, I have taken this example from the Norman and Nice. So this you might be aware of this particular diagram, but I will be explaining you. So you can see that this is a standard second order, under damped response, and this is my C final. So there are various terminology. What you can see here is TR is the rise time, TP is the peak time, settling time, output, maximum output, and the desired output. What I will say that this C final is the desired output. That means I want my system to be at C final. For example, this C final can be the reference speed of a DC motor, like 1500 RPM. What we have seen here is I want my system, the speed of the DC motor to be 1500 RPM. So this C final is a 1500 RPM. But what is happening here is initially it is going like this, and instead of settling at 1500, it has gone above the 1500 due to the various inertia elements and so on. And what is happening here, and due to the various control issues as well, the control is not properly designed. So instead of going to 1500, it has gone to 2000, and then slowly it has come down to 1400, and then it has settled. So that is fine. If you design an appropriate controller, so this particular thing from 15 to 1800, what we are seeing is this is called as an overshoot. So in general, this overshoot can be one does not want much overshoot for a particular system. That means you don't want your system to see beyond certain value. For example, if it is an electrical device, then you don't want the current to go beyond certain value. So in those cases, we have to limit the overshoot. You have to design an appropriate controller which will ensure that this overshoot can be reduced. So you can see that the rise time, in general, there are various definitions of various norms, but we will stick to this particular norm. The rise time is, this is 0.1, that means 10%. The time taken for the system to reach from 10% to the 90%, we call it as a rise time. You can see the 10%, and this is 0.9, that means 90%. So this is called as a rise time. And the peak time is when the peak is happening. The peak time when the peak is happening, we call it as the TP, which is the peak time. And the setting time, when the system settles within a certain bond of, let us assume, 2% tolerance. Here you can see that the system is 0.98. Suppose if I want 1 here, it is 98 here and 102 here. So within the 2% of tolerance, so that is called as a settling time. So whenever your system settles within the 2% of this tolerance, in some cases 5%, we call it as the settling time. Okay, so that is what about this time domain specification. So the next thing is, who will give you this time domain specification as a control engineer? If you go to the industries, who will be giving you this time specification? Nobody will give. Based upon the problem at hand, you have to select your time domain specification accordingly. If it is a very fast system, we want very fast, the setting time and so on, then you have to design the controller accordingly. In some cases, it is always possible theoretically to design a very fast, infinitely fast system, but in practically, it is almost impossible. For example, for the nuclear reactors or the nuclear applications, you cannot have the you cannot you cannot do the fusion or fission within a millisecond or so, because it has its own restrictions, or it has its own dynamics, which will not allow you to to design a particular control systems which will have such a less settling time. Though numerically or theoretically it is possible, but practically it is almost impossible. For example, if you want to go to Delhi to London, let's say, so you can say that in 5 seconds, if you can design the simulations, everything, and you can say that yes, in 5 seconds my simulations is showing the good results. But no, that is not the good thing. The systems has its own limitation, because the maximum speed of a particular aircraft or the passenger aircraft, it cannot go beyond beyond in general it is 800 to 1200 kilometer per hour. So you cannot expect that 5000 kilometer per hour, you cannot expect a particular aircraft to travel, though it is possible, but it is not always feasible. So all these constraints you have to keep on in your mind. So for the faster systems, if you want where the very fast, for example, the defense applications where every millisecond is also important. So accordingly, you have to design these time specifications accordingly. And for some systems, if it is a very slow systems, then that is fine. Then sometimes the settling time can be in the hours as well. So this time domain specifications you have to design, and you have the control engineer has to fix based upon the plant at hand. There is no such single, I want all of the system to settle at 5 seconds. There is no such single specifications available for all the whole world systems. Based upon the problem at hand, you have to accordingly select the desired specifications. And this is a very typical feedback system. You can see the similar thing what we have seen here is the plant, and this is the feedback. This is the sensor dynamics. Every sensor has its dynamics, and this is a closed loop thing, and you can see that there is a negative feedback. So why the negative feedback here? What we are doing here is error equal to reference input minus output. For example, if it is a positive feedback, then what is going to happen? Error equal to reference input plus this output. So this error signal will keep on increasing, keep on building if you use the positive feedback. That's why, and it is very dangerous as well using the positive feedback. If you don't handle it appropriately, then the system will crash, or system will become unstable. So negative feedback, in most of the cases, negative feedback is the main tool for control system design, main structure for the control design. And this is one gh by 1 plus gh. How we are getting here is just briefly we see error e of s. So this is E of S equal to R of S minus this particular signal. This particular signal is nothing but C of S into H of S. So now my E of S equal to R of S minus H of S into C of S. So what is this C? The C is nothing but this block G into E of S. So that's what we are seeing. And now E of S, whatever I have obtained here, if I substitute here, I'll get C of S as something like this. And if I rearrange this one, why I'm rearranging this one? Because the transfer function is nothing but Laplace transform of output by Laplace transform of input. So I want Cs by Rs. So I have to rearrange this term in, if I am rearranging, then I will be getting the left hand side like this, and the right hand side is Gs G by 1 plus Gh. And this is called as a closed loop transfer function because this is a closed loop one. And G into H, suppose if I'm breaking this loop here, if I break this loop here, that means if I disconnect this one, then G into H will form a open loop transfer function. And this, whatever you're seeing here is I have taken from MIT course number 2.04. This is from the MIT courseware by Professor Derek Rowell in 2008. So this is the reference for this one. So now I will be interested slowly, and now I am going to do whatever we are learning now, we are listening now. This you have to do in the MATLAB, and how to do it I will tell you. So a typical feedback control system will look like this. So this is my plant, G of S. You can see that G of S is, okay, forget about this 25. What I will say that 1 by S into S plus 5. So this K is the controller. So what is happening here is this K, if I can substitute different values. For example, I have assumed this K equal to 25. So 25 by S into S plus 5. This is a feedback control. So if I substitute K equal to 25, since these two are like cascaded, then it will become like this. So this is the control. And now what I can say that this combined plant and control G of S is 25 by S plus S into S plus 5, where K equal to 25. If I substitute K equal to 25, I'll be getting. And in this feedback loop, there is no such sensor dynamics. So what I can say that H equal to 1. So open loop transfer function, what we have seen there is G into H. So G into H is 25 by this one. And the closed loop is G by 1 plus GH, 25 by this one. So all these things you have to do it in the paper and pen. I will circulate this slide at the end of this lecture. You have to do, you have to derive on your own this simple thing. So now what is happening here is, uh, if we so this is my closed loop transfer function G by 1 plus GH, 25 by S square plus 5S plus 25. And this is the one what we have seen. This is the second order thing. If I correlate these two things, these two omega n square in the numerator omega n square, so omega n square is equal to 25, square root of 25. So omega n square equal to 25, hence omega n equal to square root of 25. So I'm getting the 5 radian per second omega. So what I told there, the important things for any typical second order systems are two parameters only. One is the natural frequency and the second one is the damping ratio. And so my natural frequency is 5 radian per second. And the damping ratio, so what I'm doing here is the coefficient of S. So 2 zeta omega n, if I'm substituting equal to 5, omega n is known to us, which is 5. So and hence my zeta equal to 0.5. If the zeta is less than, if it is lies between 0 and 1, then I call it as an underdamped system, and this is an underdamped system. I will not go into much details of what is undamped, underdamped, overdamped, critically damped, which you can go through any of these textbooks, standard textbooks. But my intention is to show you, to if you want to simulate this, to get some physical feel of the system, which we'll see. Okay. So now the peak time, these are the standard formulas. Peak time is 0. If I apply, since I have that omega and zeta from this particular slide, if I substitute here, the peak time I'll be getting like this. Overshoot also I can calculate this thing, and settling time is. What do you mean by this thing? How do you physically visualize this thing? That means if I plot step response of this particular system, then it should look like this. Whereas the overshoot and rise time, settling time, peak time, from this particular equations we can calculate. So what I mean to say here is that for this particular application, the peak time is 0.726. This is fine, but how do I get this one? How do I plot this one, and how do I visualize this one? So that's what we are going to see now, and why this closed loop feedback is required. If I don't give this feedback, then what is going to happen? All this analysis we will do, we'll see in terms of the simulation. Okay, and we'll see whether whatever the responses, whatever you have got here, the same we can see from the simulation or not. Keep in mind that overshoot is 16.3%, and the settling time, sorry, peak time is 0.726. That means whenever the system is maximum overshoot, then the corresponding time is this one, and the settling time is 1.6. That means system settles at 1.6 seconds. We'll see this one how in the coming slides. And another aspect here, so the problem there is if I take k equal to 25, then my overshoot is 16.5%. 16.3%. For the 25, you can see that if k equal to 25, which is a controller, which is in your hand. Controller is the one which is in your hand, which you can do tuning. So if the k equal to 25, my overshoot is 16.3. But I don't want this much overshoot, because this is too much of overshoot for my system. That means I don't want to go to 16.3. I want to keep myself below the 10% of overshoot. So what should be the control strategy? So here you can see that the idea here is we wish to reduce the overshoot to 10% or even less. So how do I do that one? So this is instead of 25, what I did here is I kept the k value. K is unknown now. So what I want here is omega, and I want to reduce this overshoot to 10%. But how can I reduce this overshoot? If you see this formula, this overshoot is mainly dependent upon this zeta terms. If I can control this zeta terms in some way through some mechanism, then the overshoot can be controlled. So that's what is happening. So omega n, if I'm equating to standard second order omega n square by s square plus 2 zeta omega n plus omega n square, what we have already seen, omega n equal to root over k, and 2 zeta omega n equal to 5. This is the same from this 5, and hence what I'll be getting, zeta equal to 5 by 2 root k. So if we, for the 10% overshoot or less, we need 0. From this we can always calculate zeta equal to 0.5 or more, and therefore k equal to 17.9 or less. So that means if I use this k value as 17.9 or approximately 18 or less, then we will have the less overshoot, 10% or less overshoot. This we will see in the simulation. So from here we will start our simulation analysis in a very detailed way. So this is the plant what I am interested. Okay, all of you listen very carefully. This is the open loop plant. So this is the open loop plant which I am interested. 1 by s into s plus 5. This is the same plant. So which I am calling it as a GS. Okay, we will analyze the above block diagram using MATLAB. How to do this one we will see. Okay, so this is the open loop analysis. So what is happening here is, this is the input, reference input. I have given the step of unit step with step time as 0. So and hence which will become a step, which will become a constant of 1. and 1 by s square plus 5s. So from where we are getting? So this is 1 by s square plus 5s. If I multiply s into s plus 5, I will be getting s square plus 5s. So this is 1 by s square plus 5s. So some input has been given and I want to see what is the output. So this is the open loop. You can see that this is the open loop. Some input, unit reference has been given as the input, with step time as 0, and this is the output. So what is happening here is, if I simulate this one, I will show you how to do this one. Please listen this now. If I simulate this one, then for the one you can see that the system response is going, very large, and this is a small code to plot this one. This also I will explain. So you can see that within 10 seconds it has gone to 2, and if I run for 100 seconds it will keep on increasing, and hence the system is unstable. So the open loop system here is unstable. So what we will do here is, we will try to design a closed loop control system. And this is the similar closed loop control system what we have seen here. You can see that there is a 25 gain. So gain k value is 25. This is the controller, and this is my same plant, and this is a feedback mechanism. So the unstable plant, what you are seeing here, this plant response is going keep on increasing. We could able to control something like this. However, we have seen that the overshoot of 16.3% and so on. So, but what was our learning? We have designed this k value in such a way that if we k value select less than 17.9, then we know that this is going to be reduced. So in the next simulation, what I did here is, I changed this k value to 10, and I again ran. You can see that immediately this whatever the overshoot what you have seen there is completely vanished. Okay. So only thing is I have changed this control. So this is the control action. So what is the purpose of this controller here is to reduce the overshoot. And this is the comparisons with k equal to 25. You can see how much So this has gone very large. However, the overshoot is minimal, and with k equal to 10. So this is the comparison. Now what I'm going to do here is, I will show you how to do this MATLAB in another 2 to 3 minutes, and then I will give you the videos of the simulations, how to do the simulation, and you have to do it in another 20 minutes. The video is only for 10 minutes. I will explain you everything. If you see this very carefully, you can do on your own in 5 minutes. So please ready with this things. Please listen this carefully. I will be giving you the video recording. I have already recorded the simulations which I will be giving you. Don't worry about that one. But the important thing is, you should see how the simulation has been done. So the first of all, you open the MATLAB here. You open the MATLAB. So you can see that different versions of the MATLAB will have different things. So this is the command window, current folder, workspace, and other things, which is not of much interest now. I want to develop a block diagram. If you want to develop a block diagram, you have to select this Simulink one. This is the Simulink. Just select this Simulink and open this blank model. If you are clicking this blank model, in some cases, in some old MATLAB, it will be new Simulink, new MDL file or something. Now this creates a venue where you can create a particular block diagram. So what are the things required for the open loop things? If you see this particular diagram, for the open loop things, I need a constant, I need a transfer function, I need some scope to see the output, I need some clock, and I need something you want to transfer it to the workspace. I will tell you how to do it step by step. The first thing is, what I am interested here is, it is taking some time. Let it take. So what I'm interested here is in the plant open loop. When it comes to the closed loop, I need to have this the summing block as well. Initialization will take some time in the MATLAB, but once if it get initialized, then quickly you can do all the all such kind of activities. So here what we will be doing here is three types of simulations we'll be doing. The first one is the open loop simulation, that means no controller. And the second one is the controller with 25 closed loop controller as 25 as the gain. And the third one, what we are doing here is with 10 as the gain, and we'll see the response. It is still, yeah, now it has opened, yeah. So this is my Simulink thing. And as soon as if I click this one, it will, it will show this one. So if I go to the continuous, there will be this small tiny task function, right click and add to the model. And what are the other things is required? The constant. If I go to the sources, this is a constant block, select left click and right click and add to the model. So here you can see that two things are there. So one more thing is what I required here is, if I want to see the outputs, this is the sync, add to the block. This is the output. Now I want to connect. All of you please keep like this and you can add. There are various shortcuts are available which you can explore over the time. However, this transfer function is not the one what I want. The transfer function what I want is 1 by s square plus 5s. So what I will do here is I will double click, numerator is 1, denominator is 1 square 5s, so s square into 5s into 0. So this should be, you should take care, what is happening here is 1 this in the descending order of s to s power term, s square, s to the power 1 and s to the power of 0. S to the power of 0 is 1 and there is no such coefficient, so that's why there is no constant, so that's why it is become like this. We have to write it like that. This 1 represent the corresponding term for s square, this 5 represent for 5s, and this 0 is represent there is no constant term. So if I say okay, you can see that, you know if I just drag this one and if I press the space bar button, so it will look like this. So 1 by s square plus 5s and this one. If I run this one, it is running 2%. Initially, as I told, it is a bit slow, but then it is fine. I can see what is happening here is, you can see that it has gone to infinity. If you want to have the nicer plots, if you want, the trick here is you have to transfer all the data whatever you are getting here to the workspace and then plot it. So what I will do here is I will go to the sinks, I will take this to workspace, I will keep this block and I will connect this one and I will say this is my output. I want the time because in the x-axis I want the time. There are various things here. Sometimes you don't need the clock as well, but I'm just showing the very simple thing by using the arrays. Select the array as the option. It will save in the array format. And time is also, you can get it from the source, this clock, add to the block. And this I will say it is a time, time, enter. And I will just run this one. And this small code what you have seen there, this one, if I use this code, then you will get the plot something like this. So I will just plot you. I'm not writing the complete code, just partial code. You can type this one, plot of time. You can see the time is already here, comma, output. All the variables should be the same. There is some issue there. Again, I will run this one. You should see that this should also be the array. This is array, this should also be the array. Yeah, this is the array only. So this time versus I am interested in this output. And then this will show you this error, this one. The X label, Y label, whatever we are discussing, if you type the same code, whatever, here this small code, Y label, X label, this will give you the time and output the display will come, and this line width, the thickness of this particular line will be 1.5. If you want thicker or the fatter one, you can select 3 or 5, whatever it may be, but 1.5 is the standard one. So since the system is unstable, now what you have to do here is, all of you remember that you have to save this one. You have to save in some folder. Just for the sake of simplicity, I am keeping, in the desktop, just I saved with SDP1, and I'm saving in this one, open loop, open loop one. Now what I'm interested now here is closed loop things. For the closed loop, I will save the same file as closed loop, and then I will change accordingly. So go here, save as. Now what I'm trying to do here is, I'm trying to convert this open loop to the closed loop system, and we'll see the performance. So what are the things we need that you know that to generate the error, that block, summing block? I'll go to the math operations. In the math operation, you can see this add. What I have done here is I have added. So to create the closed loop one, I will reduce the size of this one. I will remove this one, and I will keep this one. I will connect. I will connect here. But important thing here is, this is plus plus, but we want the negative feedback. So what, double click this one, and I am going to change this to minus, and this I am doing something like this. Okay, but something is missing here. The missing term is gain. I don't have the controller here. So to have the controller, what I will go to do, what I'm going to do here is, I'll go here for the math operations. I will take this as a gain block. Right click, add, and I am going to add it here. If it is not getting connected, so the easiest way is, take it out, delete this one, keep in between, and most probably automatically it will get connected. Okay. So now what I'm going to do here is, this is the 25, right? 25. If I keep the 25, and remember, if I keeping this as 25, then the peak overshoot is around 16 or so. We will see the same thing. I'm going to run this one now. I just ran, but if you want smoother plots, then you go to the settings. Just I'm trying to change some settings here. Meanwhile, so this is the one. You can see that the same plot. However, you can see that there is lots of discontinuities. So what I'm going to do here is, this discontinuities one can remove by using this variable step to the fixed step, and in the solver details you can keep you can select some solver like OD4, and you can do this one 0.01. My voice is audible. So now what I'm going to do here is okay, and then I will run, and then I will see what is happening. So now you can see that the plot is much smoother. The overshoot, if you want to see how the overshoot is, you can just zoom this one. The various zoom options are there. You can select any such thing, and just I have enlarged this one, and I'm interested in this one. So if I'm zooming this, you can see that it has gone to 1.162. So that means around 16.3. 16.3 is my I should be at 1, but it has gone to 1.16. So that means 16% is my overshoot. And the corresponding time, the time, peak time, you can see that approximately how much it is coming, 0.73 something. The same thing we have observed there as well. And you can see that system has almost settled here. So the similar statistics we can see from our manual calculations. You can see that overshoot is 16.3 and the settling time is 1.6 and our peak time as 0.726. Now what I will do here is I will change this to 10. That's what we learned. If I'm changing this to 10, so if you want to plot this one, then again you can use the same plot of, it will give you the nicer plot now. But again, what you have to do here is you should ensure that you should save this one, you should run it, and if you plot, that will be that the same plot you will be getting whatever you're seeing. But now what I'm interested here is I want to reduce this k to 10, and now I will see what is happening. So that's what we learned, that control. You can see that suddenly this overshoot has gone. Now it should be less than 10%. That means it should not go beyond 1.1. If I zoom this one, you can see that it is 1.016. That means it is 1.6%, and everything is very smooth. So what is the trick here? This is the controller. This is called as a controller design. This is a very simple controller design. In the coming days, we'll see much complex control design. The simple control design will work for simpler cases, but not for all the cases. So we'll see this one in the coming class. So what I will do here is I will be giving you a video of you please work with it. So today we will extend beyond 12 o'clock. I will give you another 20 minutes. So till 11:50, or let's say 12 o'clock we'll meet again. So after the 12, all of you should be here. All of you should be there, because after 12 we will discuss for 5 minutes and there will be quiz session. Okay. All of you have to mandatory attend the quiz session. So I'll be sending you the video link. Please go through that one and try to replicate, and let's see how many of you will be getting these results. Okay. So I'll be sending the YouTube link in a minute.
Sir,
Yes. Yes.
sir, all these saved videos will you send?
Yeah, I'm sending you how to do this one. I'm sending you right way, straight way. YouTube
Okay, sir.
video.
Thank you, sir.
Sir,
Yes. Please.
Okay, sir.
sir, after 12 o'clock,
In
there
the
is another session.
Is there?
Is there any another
whose session? No,
And
quiz will be there. Quiz will be there.
Okay, sir. Thank you, sir.
I just sent the YouTube link, tiny your link. If you click that one, it will take you to this video. Meanwhile, if you have any questions, we can have discussion for 5 to 10 minutes. The remaining people should follow this YouTube link. Is it there? I think it is there in the WhatsApp. I just sent that one. And if you have any queries, you can please. But please join back by 12 o'clock, huh? Because 12 o'clock we will have some conclusion session.
Okay, sir.
Yeah. So if you have any queries, then we can have the discussion now. The remaining, I request all of you to please do this thing.
Sir, good morning, sir.
Just a minute, sir. Just a minute. Just yeah. Please give me a minute.
Oh,
Yes. Please tell. Yeah. Please
good
introduce
morning,
yourself,
sir.
your name and your institute.
My
That's
name
it.
is
And
sir. My name is KVS Rao, sir. The Vishaka
yeah.
Institute, sir. Last
Yes.
time I
Yeah.
attended the FTV to Polytechnic College.
Okay.
Sir,
Okay. Yes.
sir, I told you, no, I'm working as lecturer in Polytechnic
Yes.
College.
Yes. You have a lot
Sir,
of experience, and then you are doing
sir.
MTech in
Yes, sir. Thank you, sir.
sorry, NSR.
So,
Yeah. Please.
sir, actually, that just to drawn that control system block diagram, sir. For that, you added
Yes,
the
sir.
time and the output, SIM output. That I just
Yeah.
please
Yes.
clarify once.
Okay. So why added that one is
Yeah.
uh, okay. I will explain you. Suppose if this is the normal Simulink diagram, if it is Simulink diagram, the whatever the output you are seeing in the black background and something is not a nice one, right? Nicer one. So
Sir,
what
screen
this
is not
two
available.
works. Okay, sorry. Yeah, I will share the screen. Yeah,
Screen share.
yeah. Okay. So now you can see that if you see this one, so it has a very
Okay.
black screen, black background, and such a thing. So what this two workspace, what this will do, this will send the variables to the workspace. The time, this clock time will be is a variable in array. The time all 0 to 10. Since I am running it for 10 seconds, so with an interval of 0.01, that's what I specify. It will be saved in an array, and this output will also be saved in an array. So later on, I can plot that one for nicer. If you want to publish in some paper or something, you want the nicer plot. So to plot that one, so this we are transforming it to the workspace, and from there we are using it for the plotting. That is the only reason.
Okay. For any block diagram, it will be the same procedure only, sir. Whatever the
Yeah, it will
variables
be
you
the
want,
same.
for that we have
Yes,
to.
yes,
At
yes.
a
It
time
will be
only
the
we
same
can
thing.
take only two, no, sir.
No,
X-axis,
no, no.
Y-axis, only two.
Infinite, infinite, infinite. I can
Any.
keep the
Okay.
I can keep the some output, but the variable name should be different because
Okay. Okay.
the
We
signal
have
what
to
you are
select
getting
the
here
name.
and here are different. Yeah, you have to rename
Okay,
that
sir.
value variable with different name.
Okay.
Yeah.
So according to our requirement, we have to change it. Sir.
Yes, yes. You have to change.
Thank you. Thank you, sir.
Yeah.
Sir,
PPTs I will be
hello,
sharing you, and yeah, PPTs I will be sharing you, and this already I shared you how to do this one.
hello, sir,
Yes, hello.
hello. So why
Yeah,
we
yeah,
prefer
please.
negative feedback, sir? In why
Sorry,
we
sorry.
prefer negative feedback? Why we prefer
Because
negative
if we,
feedback, sir?
yeah, 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 I explained. I will explain one more time with this one. If you see this, let me share my screen now. Sharing the screen. A very simple answer to that one here is, if you see this particular block diagram, you can see that error signal is nothing but R of S minus of H of whatever the signal is coming from here, which is nothing but H of S into C of S. I will assume it as Y. So what is happening if it is negative, then my error, you are subtracting this from this. So the error will keep on reducing if your controller is designed perfectly. If it is a positive, then what will happen? Error equal to Rs plus whatever the signal you are getting is Y of S, let us assume. So error will keep on increasing, isn't it? So that's why to reduce always this error, so we are going for the negative feedback. If you use the positive feedback, obviously you are adding two particular values, and hence the signal will be, I am assuming that both of them are positive in a very naive case. So the signal value will be very high. Otherwise, if you are subtracting, then obviously the error will be reduced. So just to reduce the errors, we always use the negative feedback.
Okay, sir. Thank you, sir.
What is that plus minus? Plus minus is nothing but the error detector. So this is the one. So this you what you are seeing here is round one. I use the square one, but you can convert it to the round one as well. If you double click that summing block, so that summing block or the error block, this is the error generator or the error detector. So it will detect the error between this reference and this whatever the output, and it will generate the error. Why we consider only step response? Uh, because step response, these are called as the standard test signals. Generally, the step, ramp, and sinusoid are the three standard signals what we use in throughout the control system designs. If we want to go for the time domain analysis, that means if the input, whenever I say the time domain response or the time response, always in the x-axis you should have the time terms, and when I say that the frequency domain response, the input should be, if it is a sinusoid signal, then whatever the output you are getting, the relation between the output and the input, if you plot in the magnitude as well as the phase, we call it as the frequency response. Or if it is time domain, we generally prefer the step signal or the ramp signal, because step signal is such a standard signal that it is a sudden increase, suddenly based upon the, if your system can withstand this kind of sudden change in the input, then obviously, which is that's why we are calling it as step signal. It can handle any slowly moving inputs as well. That means what we are doing. And suddenly here I have assumed that the step time as 0. However, if step time is 1, then what will happen is 0 to 1. If the time is 0 to 1, the output will be 0, and exactly at 1 there will be sudden spike. So what we are doing there is sudden, we are seeing the response of the system to the sudden change in the input. So such kind of sudden change, if your system can handle, then obviously any such any kind of drastic changes it can handle. So that's what in general we call it as a test signal. The block which is used to join the network is called summation block. Yes, summation block. Yes. So the plus and minus, you can use summation block. Yes. So plus and minus, plus is generally that one. You can use plus and. Can we give impulse? Yes, that is also called. We can give the impulse as well. But practically giving the impulse is almost impossible. Practically, impulse signal is very impossible. So what is the impulse signal? When t equal to 0, exactly at t equal to 0, what you are saying that the if it is unit impulse, the output is 1. But practically, generating the impulse signal is almost impossible. At t equal to 0, you cannot generate the perfect impulse signal. So people use the impulse response as well, because impulse response and this transfer function is almost they have the good relationship between. If you excite the system with the impulse response, then output of your system will become the transfer function. Why? Because the Laplace transform of impulse is 1, so that's why output by input, output by 1 equal to your transfer function. Your transfer function is nothing but the output of the system. Exactly. I hope all of you are going through these videos. In all blocks, we have standard equation for TSPs per unit only. Please give ramp also. Sir. Yeah, you can give the ramp input as well. So there is no harm. You can. In all books, we have standard equation. No. There is for the ramp also. If you see the very standard response, standard textbooks, I'm not sure which textbook you are following. The ramp analysis is also been given in the textbook, or you can derive on your own. It is very simple. Instead of in the denominator r of s, instead of step, if it is step 1 by s you are taking, you can take 1 by s square and you can derive on your own. Sir, can you explain the same format of workspace block like time series, structure with time, and array? So I have taken the very simple case of array. If it is time series, then the time will also be saved, along with the particular value. So you don't need this clock and another one. Why I used the clock and other things? Because in some of the older versions you don't have this time series one, you have only the array. So that's why I have taken. And the structures you can save, if there are lots of variables, then you can save, if your output, whatever you are trying to capture is have lots of variables, then you can save in the structure as well, like output.x, output.y, output.z, and so on. So it will be easy to plot. And structure with time, suppose if you want to plot the structure values, and if you don't want to use the additional clock whatever we are using, then it will have that structure with time as well. Sir, is impulse response is used for stability analysis? Yes, impulse response is nothing but the transfer function will become your the output. Yes, it can be used for the stability analysis as well.
Sir,
Can I use to? Yes. Hello.
sir, for array, it only takes only integers only, sir, for time. Integer
No,
values
no, no.
time.
Anything. No, no. Yeah, any values it can take based upon what is the sampling time you are giving. If you are giving sampling time as 0.01, then if you're running for 10 seconds, it will keep on saving value 0.01, 0.02, 0.03 up to 10. So that based upon, what you can do here is you can just run this one, and in the workspace, you just type time. It will show the complete time vector. I will show you now.
Sir?
Share the screen, sir.
Yeah, I will share you. Yeah. Just let me, because I closed something, I want to open it. Okay, so I'm sharing the screen. I will show you. So this is the one, something I ran for this open loop. I just ran here. So the variables, you can see the T out, time, and output. So if you just type time, it will show all these values, whatever you have there, So the complete thing, 0.002 and so on. So various things, it will be there. If you are using the fixed time steps, like what I told here, if you use this fixed time step,
Sir?
then it will be distributed linearly.
Sir?
So what I'm doing, yeah.
There is we should initialize any data type, sir, for time.
No, nothing is required. Automatically it will take. I'm just running this one, and automatically it will take. I will show you, I you can see that I gave as 0.02 as my, so time 0.0 to 0.04, something like that, automatically it will be saving. And the corresponding values are also, you can see that the corresponding values for those particular interval values only will be saved accordingly. So this is the one. So whatever is here, so you can see the same thing. If you type, yeah. So I suggest you please go through this video, because in the video everything I have explained you. It is hardly a 10 minutes video. You go through that one, and then the simulations, it will be more. You will get more exposure to that one.
Sir?
Yeah.
Sir? Why should we use timer,
Yeah.
sir?
Sorry. This
Why
time,
should we use timer, sir?
because if you want to plot here, if you want to plot time versus output, you need some time value, right, in the x-axis. For that one, we need the clock.
Okay, sir. Thank you. Sir?
Yeah. Hello.
So normally in textbooks or in any another materials, timer is not placed, no, sir.
No. For the simulation purpose, you need it. If you not, you use the array with how in the normal textbooks, what is the x-axis? X-axis is the time, right? Isn't it?
Yes, sir. Yes, sir.
So this timer is just to, if you don't keep the timer, if you can just see that scope, in the scope, everything will be there.
Yes, sir. Yes, sir. Yes, sir. Thank you, sir.
Okay. why should we change the solver? The solver, basically, if you are using the variable time step, then what it will do is it will solve by using the various time step. Because if you see the numerical solutions, every time we have to use some kind of what I mean to say, that step time to solve that one. But in some cases, what is going to happen is, if you want to solve a particular equation for a particular range of values or for a particular situations, then you may need smaller time step, and for some equations or for particular operating, then you may need the larger time step. So that is called as a variable time step. However, if we want, in most of the cases for the practical applications, we use the fixed time step. In the fixed time step, what we will do is we'll try to capture the data at a fixed time step size. Suppose if your sensor he has certain data transfer rate or some particular frequency at which it transfers the data, then we have to capture the data with that particular uh, by we have to capture, we can only take the data in that particular instant of time itself. So that's why we have to use the fixed time step. The smaller the time step, the more accurate data you will get. That means for those particular time steps, means if it is very smaller, for each of these steps we will be having the data. If you take the larger time steps, that means you don't have the accurate data in between two particular time samples. That means if the time step is 0.1, that means if I am running for one at 0.1, 0.2, 0.3, I have the only data for that. If I plot that one, then it will not be smooth. However, if you want the accurate one, the smoother one, then you should have between each of these, the smaller the time step, it will be good. Why we change the solver? Yeah, is it necessary? If you want the smoother plots, then you need to change that one. Otherwise, you don't need. Okay, so welcome back. So we are coming back now. Can you please, how many of you have at least simulated the open loop response? Please put in the chat box. How many of you? Yes, completed, done, done. Good. Good. Okay, first one done. Okay, good. So I think some of you can do it, and the others, since the video recording is always there with you, you can always use that one. So what I want now here is, every day I would like to take the group pic. So I request all of you to keep your videos on for 10 seconds. That's it. So I will take a screenshot and just I will keep it for my records. All of you, please keep your videos on for 30 seconds. What about others? You don't want to share the cameras, or you're not there, or just for a minute, then you can switch it off. Okay, thank you all. Now you can, if you want, you can switch off your cameras. Okay, so now we will have the conclusion and what need to be done for tomorrow's some small assignment. I think this is the one. So what is the learning before going to the assignment? What is the learning and what is the summary of this particular? So we have started our discussion with open loop control and closed loop control and a small controller design as well. So we have done with the numerical way and we have seen in the simulation as well. To start with that one, so this is the basic block diagram. This is the open loop control and this is the transfer function. So what we have seen here is in the open loop control, the system is unstable. It is going, the system response at least is unstable. You can see that what is happening. This is keep on increasing and increasing, but we don't want this one. So the next is we have gone for the what I can say that we have gone for the closed loop thing, and we have designed we have substituted some k value, which is giving the peak overshoot of around 16% or something. But as a control engineer, my desired reference, my desired specification is the the peak overshoot should be less than 10%. For that, we have designed manually, and we have come up that if it is less than 18 or 17.9, this k value, then it will be less. So I selected this as 10, and you can see that this one. So this is what you can see, and this is exactly called as proportional controller. Tomorrow we are going to discuss PID controller, proportional integral derivative control. What is the limitation of this proportional control? What are the advantages of others, and how to design? We will see tomorrow. So this is the summary. However, the assignment here is you have to design the similar. You have to do the open loop analysis as well as closed loop analysis for a double integrator plant. What do you mean by a double integrator plant? That means the plant is nothing but 1 by s square. So two integrator, if you connect in cascade 1 by s and 1 by s, so that will become 1 by s square. So my plant g of s is 1 by s square. And then you have to do the open loop performance and the closed loop performance with different types of control gains. So what today we have done, I have given you the videos as well. The similar, I will share you these slides as well very soon. So that is the today's assignment. So that's it from my side. If you have any quick questions, I will take a couple of quick questions and then we will start the quiz exam. Quiz. Anyone? Anything? If if there are no questions, then I'm sharing you the quiz link now.
Actually, sir.
Yeah.
Sir, while drawing that
Yes.
exercise, to connect that output to the workspace, I am not getting that, sir. Actually,
You're not getting me?
but connecting that output line to workspace. So by clicking that line, joining that line, I am not getting. Is there any wrong thing I'm doing, sir?
No. You should get it.
Okay.
You should.
But
You should get
other
it.
lines I am connecting, but I'm trying from difficulty in getting connected. It is coming in red lines, sir. That's why. While showing that output
Hello.
to workspace. Hello, sir.
Yeah. Please tell, sir. Yeah.
That while drawing that output to workspace, I'm getting some red line. It is coming, sir. It is not connecting the.
Then you have to connect it, sir. Then you have to, you have to
Only just
adjust
try it.
accordingly.
Okay.
Yeah. There is no.
I will
There
type
is
right.
nothing wrong in that one. You have to connect. You have to
Okay.
connect.
Okay. Thank you.
Yeah. Hmm. Okay, guys. I already shared you the link for the quiz. So please submit this quiz. And somebody has told that, are you going to give the theory on why PI and PID? Yes, tomorrow our whole discussion will be on PID control itself. So if you have not gone through the PDF file which I shared, the instructions in that one, day 1, day 2, day 3, everything I have tentatively I have given what need to be covered. So you can go through that one. The PDF file. I'll be going to cover P, PI, PID in very detailed. Somebody has said that, sir, I don't have MATLAB license. See, this is what I cannot. I'm helpless. So that's what I told. That's what I have mentioned the flyer as well. MATLAB is required for the hands-on. So if it is not there, I'm helpless, because that is one such a thing which is required. Otherwise, you can only listen the classes. You will not get the real feel of doing the simulation. You can ask from your friend, and where do we have to submit the assignment? This assignment is just for your practice itself. Tomorrow, I will randomly ask someone to present that one. Impact of double integrator. Double integrator is an unstable plant, and most of in some of the real life examples like launch vehicles can be, or in some cases a simplified DC motor or some other electrical applications, one can easily can be represented by double integrator plant. And it is a very unstable plant, so this is a very critical plant which need to be controlled. No webcam in my desktop, sir. What is solver, sir? Already I discussed about the solver, Niharika. Okay, so this is from my side. So tomorrow we will discuss with more, uh, other things. I will keep the WhatsApp group open for your queries. And again, I will log if I want to pass on some important information, so that, you should not miss that one. So I'm just opening that, allowing users to interact among yourselves as well, peer-to-peer learning. So that's it from my side. So thank you all. So all of you, please complete. Sir, share MATLAB download link. This I don't have, Vinay. I don't have this one, which is around 20 GB. Maybe in the group people can share, because most of you will be having, your friends might have that one in the pen drive. You can take it from them. Okay, so I am ending this session. So tomorrow again we'll meet at 10 o'clock sharp. I will open the link by 9:45, 9:50 or so. I'll give you the link. Please attend. Thank you.